test. Oh. All right, so we can start. So, hello everyone, I'm Artur, and welcome to the third web3.krk meeting here at Software Mansion office in Kraków, Poland. I'll be your host for your night, and I'll be having a talk in a moment, after the first talk. But first, some organizational things. So first of all, in the kitchen behind me, there is a fridge with beers and other drinks, so feel free to take anything during the talks or after them. We'll have pizza after the talks, and there will be some time to just socialize and talk after this, so make sure to stay with us. There will be 2 talks today, both of which should take around 30 minutes. I don't think we'll have a break between them, but there will be some time for questions after each talk, so please go ahead and ask them. If you want to go to the restrooms, these are located just close to the elevators, so if you go to the entrance and turn left, there will be restrooms there. I guess that's all for the starters. And first of all, Kacper Kozioł from Herodotus will be joining us for the talk about storage proofs. So take it away.
Can we get the slides up here? Cool, awesome. So hello everyone, I'm Kacper from Herodotus. And today I'm going to be giving kind of like an introduction about storage proofs and how they enable like smart contracts to be able to read current as well as historical data in also a multi-chain, cross-chain fashion. And yeah, awesome. So to kind of understand the value proposition of storage proofs, we have to kind of understand how we got here. Like, how did Ethereum begin and how it evolved to where it is today and where it's going in the future. And the way I really like to describe this is looking at it from a smart contract perspective. So let's say you're a smart contract in the early days of Ethereum. If you wanted to access on-chain data, you had access to all the data because everything was in a single domain. And there was no L2s, there was no L3s, etc. And over time, as Ethereum had to scale, layer 2s kind of took over a big amount of the demand from block space, etc. And today we have an ecosystem that is filled with different new L2s that keep coming out, and L3s are also becoming more popular, and that's kind of where we see Ethereum tomorrow. Now, as this fragmentation has occurred, we can kind of visualize blockchains as databases, meaning that they store data in a structured manner in a consistent way over time. And these databases are containing different types of information. So we have like liquidity that is represented in different smart contracts on different chains. We have NFT collections that are deployed across multiple different layer 2s, as well as things like name service providers. Like we know today that there's many of them out there. We have like ENS, which is the most popular one, but there's different new chains that have Polygon name service, Darknet ID, etc., etc. These services exist because it is very difficult to access the data that is currently on L1, and especially for the smaller applications that are in need of more exotic and granular data feeds, those are very difficult to obtain. And then we also have the rise of like social networks like Lens. If you want to create and start creating Lens content that is currently done on Polygon, you do not have access to that data on let's say Ethereum or other L2s. So how do smart contract developers deal with this fragmentation and the fact that this data is not easily accessible? So 2 main approaches are kind of like adopted right now. We have oracles and attestation networks, as well as L2 to L1 messaging systems. So let's look at each one of them. So oracles and attestation network system. Well, how do they work? So essentially, oracles, we have external parties that look into an archive node and are observing what's happening on the blockchain. And based on that type of information, they provide attestations. They're like, I'm saying that this is correct, and I'm providing my signature on top of this data. Then this data is then, the signature as well as the data is taken to this other domain, And the smart contract that ingests that data is essentially checking the signature of that party, or the signature is multiple. And if they are correct, the smart contract can start executing logic. But the key property here is that the integrity of the data that is being signed is not verified. And even though it's very unlikely, if an oracle is designed in a proper manner, there is still potential for someone to sign, even if it's accidentally, information that is incorrect. And this risk exists, and this risk has been a trade-off that many of these applications that rely on-chain data have been taking. So the second approach that we have is the native system, so the native L1 to L2 messaging systems, and vice versa. You can send also messages from L2 to L1. Now, these are usually provided by layer 2s and L3s, etc. And they can be kind of viewed as, I like to view them kind of like a tunnel. There's a limitation on the bandwidth. If everyone's using these systems, if the cost of them goes up, and every single application that wants to deploy things on L2 will have different requirements for how much data they need to access, as well as the frequency at which they need to access this data. The UX of these systems is also not amazing. It's because you have to invoke these messages to be sent, let's say, on an L1, and there's this bandwidth limitation. So, storage proofs. What are they? Let's start off with the definition. At Herodotus, we define storage proofs as a combination of inclusion proofs, so like proving that a specific element is inside the data set, and computation proofs, so validating the multi-step workflow. So depending on what types of data you want to access, the workflow you will be taking is different. So we'll look into a diagram of that later on. But essentially what storage proofs allow you to do, they allow smart contracts to access arbitrary elements inside the blockchain in a cryptographically verified and secured manner. So they are the highest level of security you can have for accessing any type of on-chain data. The key feature of storage proofs that is really kind of like an innovation is the fact that they unlock 2 new dimensions. So we have this fragmentation in the Ethereum ecosystem, and we like to explain it as storage proofs unlock space. So they allow these different domains to all of a sudden start reading data that is located elsewhere. But they also have this key property that they allow smart contracts to read data that is back in time, historical data. So a storage proof, once you generate it, you generate storage proofs off-chain. In order to verify a storage proof, you need to have something to verify it against. And this piece of, it's like this initial commitment can be something like a block hash. It can be something like a state root. And it's going to vary based on what's your goal, what piece of information in a blockchain you're trying to access. So to visualize this is the anatomy of an Ethereum block. There's some simplifications, but this is what it generally looks like. And the key property that you can see over here is that on the left side, we have the block header. So all the elements that are located inside the block contain, let's say, a state root, which is like a hash of the root of the state tree. We have the receipts roots, transactions root. And depending on what type of data you want to access, you will have to take a different set of steps to get there. So over here, I have a simplification of a 3-step storage proof workflow for, let's say, you wanting to access data that is inside the state tree. So for this example, I'm going to say, let's say we want to access someone's USDC balance. So the storage proof workflow is as follows. The first thing we need is we need to have a block hash or some sort of initial commitment, which we can retrieve from the EVM directly if it's recent, right? So we'll get into the historical data part later on. But right now, if you want to access current data, you can simply invoke the block hash opcode within your Solidity smart contract and have a block hash that you can verify a storage proof against. But the next step is proving that the existence of an account. So what good for us is a storage proof for, proof for your USDC balance if at that point in time the USDC contract didn't exist, right? So we need an inclusion proof that showcases, hey, inside this world state tree, that is the middle one on top, at that point in time, the USDC smart contract has been deployed and it exists inside this block, given that previous block hash that we have retrieved directly on chain. And then finally, once we have proven that the USDC smart contract actually exists, we want to be able to prove specific data inside that account. So we want to prove, let's say, your USDC balance. So in this 3-step process, we showed that we're able to generate a storage proof for something, let's say, like a balance. But you could also kind of stop in the middle, and instead of essentially doing a proof of your balance, you could prove your nonce. You could prove the code hash, or you could prove a balance. Pretty much any single thing that exists inside an archive node is provable. If you wanted to prove, let's say, receipts, you could do the same thing, but instead of having to generate a proof at the very end for your USDC balance, you would simply go take the root of the receipts tree and be generating, let's say, an inclusion proof that a specific receipt is inside there. So it's going to vary based on what type of data you want to access. But the key limitation over here is, again, the fact that we were verifying a storage proof against the block hash opcode, which is very recent data. There's only the last 256 blocks that are accessible for us in this manner. And the key innovation that we have created at Herodotus is something we call the Merkle Mountain Range, the historical block hash accumulator. And what this really is, it's proving the continuity of the chain. So kind of let's go back to basics. A blockchain is a linked list. What does that mean? It means that the hash of the previous block is always included in the next block as a parameter inside the block header. We kind of saw that on the top left over here. The parent hash is over there. It's the second element. So what does this mean? If we have a recent block hash that we're able to retrieve from that block header right now, natively from the VM, off-chain, what we can do, we can utilize zero-knowledge proofs and a lot of fancy cryptography to be able to prove the linkage that this recent block hash we have is actually connected to, related to this genesis block. And the way we do this is with this off-chain prover. So what we really do is, at the very beginning, we let's say take a starting block. Over here we used block number 18 million. And what we do is we compute the block hash. We take that block header, we compute the block hash using that block header, and then we compare it to the parent, like the hash of the previous block. And we also generate a corresponding proof of that computation, that we have actually done this computation correctly. And we recurse through the whole blockchain all the way back to the genesis block doing this. So this was a huge event that we did, I think back in September of last year. And we keep growing and adding these elements that have already been proven and have been proven to be correct using zero-knowledge proofs into this tree, which is called the Merkle Mountain Range. It's a Merkle Mountain Range, kind of looks like mountains. And the reason we use a Merkle Mountain Range is because it's a very append-friendly data structure that allows us to continue growing it in the future. So the blockchain never stops, unless we're talking about some specific blockchains. The blockchain never stops, and it's a fair assumption to say that it's always going to be growing in the future. So we want to make sure that this off-chain data structure is ready for us to continue adding elements to it. So what we have at the very end, once we complete this whole process, is we have this big tree where we're able to compute one final MMR root. And what this MMR root really allows us to do is it allows us to prove that any historical block hash is located inside that tree. And thanks to that, we can send that MMR root directly on-chain. And once it's on-chain, we can verify that that historical block hash is actually inside that data structure. And thanks to that, we can start verifying storage proofs for historical data. And what we really achieved here is we allow smart contracts to access a dimension of information that they previously never had. So smart contracts right now and developers have mostly been exploring different types of use cases that leverage data that is available. But right now, they leverage the data that's available in state, and storage proofs kind of unlock this full dimension. But how do we know this tree has been computed properly, right? So I previously mentioned that we are including corresponding proofs of the computation that this tree was constructed correctly. And we do that using the Starkware Sharp. So the Starkware Sharp is the Starkware shared prover. It essentially allows us to take all these ranges of different blocks that we have accumulated off-chain and send them on-chain to something called the Starkware GPS statement verifier, where they are verified to be correct. So essentially, if we want to make sure something's included inside a Merkle Mountain Range, inside this historical block hash accumulator, we need a corresponding proof to show that. And that way, we can trust that that's root of the MMR. So once we have that final MMR root, we then have this cross-chain element to this. So we can use storage proofs to verify data on the chain that we're on. We can verify we can use storage proofs to verify historical data and read historical data that was on that chain, or we can actually send that MMR root to different domains, right? So we can send it to Ethereum, we can send it to Starknet, we can send it to other layer 2s. And once that MMR root is located on those layer 2s, using the same techniques, we're able to take storage proofs and verify that data exists in a different domain without actually having to send that data there. So what do we solve? It's like we previously, when I went through the L1 to L2 native messaging systems, I said that there's a bandwidth limitation. And what that really means is that if everyone was using those native messaging systems to send over the data, it would clog the system. Every single application has different needs for how much data they need to send. But using this technique, we can still utilize these L1 to L2 native messaging systems, but we use those native messaging systems to simply send over this initial commitment that we require to verify storage proofs against. So that could be a block hash, it could be something like an MMR root, etc. So this way we have solved kind of like cross-chain data. And yeah, this kind of brings me finally to be like, okay, so it's cool technology, but like, what can we build with this? What is some exciting stuff that we can do? So cross-chain data access would allow us to do things like governance, right? So we're working right now with Snapshot team to enable you to vote on Starknet based on assets you have on L1. Currently, if you want to be participating in on-chain governance, you most likely have to vote on L1. Or if you want to, you can bridge your assets to an L2 and vote there, but that has an assumption that the community supports that, and that also assumes that you actually want to keep your assets there. Either way, both of those use cases require you to still interact with the base layer, which is very expensive and unaffordable. Using storage proofs, what we can do, I can simply generate a storage proof that says, hey, you have 100 tokens on L1, and based on that storage proof, you vote on the L2 without ever having to send arbitrary message passing or like messages through that L1 to L2 native messaging system. And yeah, so cheaper voting. We can use this to prove, let's say, inactivity of your wallet. Let's say you lost access to your storage proof enabled wallet, like a counter extraction wallet, and you can showcase that last year your nonce was, let's say, 17. And today it's also 17. And based on a storage proof that showcases that your nonce hasn't changed, you have an inactivity proof, right? So you can prove that and trigger a dead man switch. We can do things like for applications for finance, do like cross-chain lending and similar. Gaming, right now, most likely if you want to have a game, you kind of have this trilemma of like, oh, you need to go on a chain that has cheap fees, but you also, at the end of the day, you're trying to participate in like a liquid market, so you want to be able to sell in-game assets. That limits you to which chains you can go to. With storage proofs, what you could do is you could like launch your own L2, your own L3 app chain, and simply tell your users that like, hey, I've deployed NFT collections on these different chains, and as the game operator, I will be relaying storage proofs to my chain such that I can verify that you actually own those assets. So let's say you have a Bored Ape or some sort of very expensive NFT. You might not feel comfortable bridging to a brand new chain or app chain that just dropped. So what you could do is you could simply generate a storage proof that, hey, I actually own this asset, send storage proof to that app chain, and start using it in-game without ever putting it at risk. So a key property of storage proofs, to kind of finish up this talk, a key property is that storage proofs really separate the utility of your on-chain assets as well as their economic value, meaning that you're able to reap utility from the assets you hold without actually ever having to move them. And this is a pretty breakthrough thing in crypto, and I think over the course of the next few months, we're going to see a lot more adoption of this. But yeah, I'll be around here, and if you have any ideas for projects or use cases that could leverage storage proofs, I'd be happy to kind of discuss them with you. But that's pretty much the whole talk. If you have any questions, I'd be happy to take them now.
Do we have any questions, maybe? All right. Well, then, thank you, Kacper, for the talk.
Thank you.
And I guess I have to take my own laptop. All right. I won't be introducing myself. I'll just start, since I already had introductions. All right, so we had a very technical talk. So now I'll start with the second talk, which is understanding MEVs. So it'll be like a bit of finance side of blockchain oriented talk, but just a disclaimer, I've had to learn all about these stuff. I'm also a very technical guy, so bear with me. We'll get to what is MEV in a second, but first, like an intro of what's the background for that. So even in normal markets, as well in blockchain markets, there are opportunities for extracting additional profits by making transactions based on behavior of other users. And some of these opportunities are like perfectly normal thing and perfectly valid, and some of these kind of take advantage of the users. And since blockchain is a very different space at traditional markets, there are some very different opportunities for this stuff that would be like illegal or impossible on normal markets. So first, let's look at how you could extract value based on some things in the market in the normal currency market. So first of all, there is arbitrage. So basically, if you look at a formal definition, it's like take advantage of a price difference in two or more markets. So arbitrage is like a perfectly normal thing, and it makes market more efficient because it eliminates price differences between markets, and it's usually perfectly legal. So arbitrage could look like this in a very high-level overview. So there is I don't know, New York Stock Exchange where some stock one sells for $185, and there is market two when the same asset sells for $190. So we could buy the asset on one market and then sell it at the other, have $5 profits, the prices equalize between markets, that's a good thing. So opportunity for that exists on the blockchain. But this is like a very basic thing, so that's already happening on markets. So there is also a thing called front running. So front running is making trades based on private information about future transactions. And in standard markets, it's absolutely illegal. So if you look at basically the same example, on the standard market, there has to be somebody that facilitates these transactions. So usually there is a broker. So as we know that if the user, also in a very high level overview, if the user buys the stock from the market one and sells it somewhere, the price will change. So broker knows that this price will change. So what the broker can do is they can, knowing that the user is making this very expensive trade, they can buy some assets for the lowest price first, then let the user make their trade so that price changes, and then they can sell and have a higher profit than the user. And it is completely illegal in most standard markets. But as we will see in a moment, it's happening in a blockchain, and there's no regulations, and the transactions are public, so why not act upon this knowledge? So, actually, I show you the old version of these slides. Never mind. What is MEV? So MEV used to refer to the Miner Extractable Value. But the opportunities for extracting MEV also exist in the proof-of-stake markets like Ethereum. So the name was changed to Maximal Extractable Value. But basically, what MEV refers to is the maximal profit that can be extracted from the block in addition to normal block rewards. Because for most often in the proof-of-stake or proof-of-work blockchains, there are some rewards for producing blocks that the miners or validators get. But also, you can do some additional things to get an extra money from the block. So in case of Ethereum, there is a concept called mempool. So transactions are submitted there, and they are visible to all network participants. So if you send a transaction, of course, eventually it will be submitted to a block. But for it to be submitted to a block, you have to show to all the people in the network the transaction you want to make, so they can actually take it and include it in the block. But there is a problem with that. If you put your transaction in a mempool, and usually it's a requirement to have your transaction included in the blockchain to put it there, everybody can see what you want to do. And it opens opportunities for kinds of front running that wouldn't be possible in normal markets, and it opens them to basically everyone on the chain. So there are many kinds of extracting MEVs and many ways to do so. And I guess the simplest way to understand how extracting MEV works is a sandwich attack. So bots or just users of the network can see your trade that buys an asset, but they can wrap your trade in their own trades, creating a transaction bundle which results in a profit to them. So for example, if we look at this, assume ETH is priced like $2,200 per one ETH, and there's one user that's making a very big trade for 2,000 ETH. So whatever they want to do with that, but they are making this trade. So they have to submit this transaction to mempool. And now everyone knows that this transaction will be executed eventually. And this is a huge transaction. 2,000 ETH is a lot, and it has to influence the price. So I've overblown the differences in prices a little bit to showcase it. But basically, what bot could do is that they see that you want to buy 2,000 ETH, so they can insert a transaction to buy a little bit of ETH at the lower price, let you do your own transaction at a little higher price because they influenced it, and then sell the ETH at an even higher price because your transaction influenced the price of the asset. So they just take your transaction and bundle it in their two own transactions, submit the whole bundle to the mempool, the block validators take that, executes that, and you end up losing some money because you pay more for the asset or you get less of some asset for the same price. And the bot results in profit because now for this example, with overblown prices, you lost 2,000 USDC because the price increased, and the bot got 20 USDC for basically nothing, submitting the transaction, minus the gas fees. So that's a sandwich attack. And it's happening. What it means to the users is that there is an invisible fee introduced to the trade, because bots like this already exist, and they make lots of these trades. So usually, your transactions end up getting wrapped in this. And also, it increases network congestion, but we'll get into that in a minute. So there's also a concept called bidding wars that is related to MEVs. So if I can make a bot that wraps your transactions in their own transactions to extract profit, everyone can do that, right? So there's incentive to everyone to make these bots. So if bot submits a transaction, like I showcased before, a bundle of transactions to extract some MEV, and the other bot sees that there is also an opportunity to extract MEV, they can submit the same transaction. But what they do is they increase the gas price they are willing to pay. So what the first bot is going to do is then they are going to resubmit the transaction with even higher gas fees. And this ends up in a bidding war or a bot auction. There are different terms for that, but basically bots will resubmit the same transactions with higher and higher gas prices until eventually one of these gets included. And what's end up happening to all users is that the basic gas price in the block is increased. So everyone pays more and bots just extract the value. Validators or miners benefit from that because they get more from the fees from the block, but for the end users, it's just more congestion in a network and higher gas prices. So it's not good. But these were all monitoring specific trades and sandwiching them in some transactions. But there are also something like generalized front running. So there are bots that monitor transactions, not just the trades on specific DXs or whatever, but all transactions. Replace the addresses in the transactions with their own addresses, simulate this transaction, and see if they get any profit from that. And if they do, they resubmit your transactions, but with their addresses replaced and with a higher gas fee, so they basically snitch your transaction from you. And that sounds like a very weird concept, but it's happening. So there is an article called "Ethereum is a Dark Forest." I recommend reading that. It's a very short article, but it explains the concept in depth. But there was some, it happened in 2020. Some user locked up $12,000 worth of token in Uniswap v2. There was a white hack attempt to restore the tokens that user accidentally locked in the transaction. So the guys prepared the transaction that would unlock these tokens from the Uniswap contract and send it back to the user. But what ended up happening is that the generalized front-running bot snitched the transaction before they managed to get it executed, and the bot got $12,000, and it was lost from the users. So it's actually happening. Yeah. But it was talking only about bots, but they're block validators or miners, and they can also benefit from MEV. So usually, there's like no in case of Ethereum, nobody is enforcing that in the protocol. But how most block validators work is they include transaction based on max fee you are willing to pay. So if you pay more fee, there's a higher chance of your transactions being included from the mempool. But nothing from the protocol enforces that. So why not extract MEV if you're a block validator or block miner? You can do that. Why not? So it's actually happening. So it's even easier and even better for the block validators because they can include their own transactions without paying any fee because they are including their own transactions. But also what they can do is they can reorder transactions, or they can even reorder the whole blocks to extract more value. And this is also problematic. So for example, reordering transactions and sandwich, like if we had a sandwich attack from the previous case, it would have to happen in mempool. So the bot would sandwich the transaction in mempool, submit the bundle, and it would be included in the block. But if you're a block validator and you have like these 3 transactions, and there's opportunity for sandwich attack, what you can do is you can just include your own transactions in the block for free and extract MEV like that. And when there's even more opportunity to, I don't know, there is something happening between transaction 2 and 3 that ends up lowering the asset price, what you can do is you can do this. You can reorder the transactions and extract even more MEV. And there's nothing in the protocol that prevents you from doing that. And that's just reordering transactions within a block. But also there's a concept of reordering blocks, which is like very problematic. Because, for example, if we had a block 1, which had like $10,000 MEV opportunity, and all block had like base 100 reward for just creating them. The validator 1, in this case, extracts $10,000 of MEV, creates a block, creates another block, and what an honest normal node would do is they would create a 3rd block on top of these 2 and just get the $100 reward, which is like what we expect to happen in a blockchain. But what's preventing block validator 2 from creating a fork? So they recreate block 1, take the MEV to themselves, they create block 2 on top of that, and then they submit their own block on top of these blocks. So now they have the longest chain. So basically there is an incentive to other nodes to now start treating the block, like the validators to chain as a valid one. And also, there's nothing in the protocol that prevents you from doing that. And if you convince enough nodes to like believe your chain is valid, they will include that. So this is like very problematic because it causes consensus instability, and the blockchain has to reorganize. All the nodes have to reorganize their blockchains. So this is just plain not good for the users, but for the validators, like they got their $10,000 in MEV, so it's good. So these are like kinds of MEVs attacks. So what are the consequences of these? So you could argue there are some advantages of the MEV. So obviously, these bots do something like arbitrage, and arbitrage is normal in healthy markets. So it increases their efficiency. So that's good. And also there is an incentive to validators to create blocks, because as we've showcased before, there can be a case where the MEV from the block is much higher than whatever the rewards are. So the block creators are incentivized to create the blocks. But from what I've looked, for the end users, these are basically only advantages that exist. But for the disadvantages of the MEV, for the user have more expensive trades. The network congestion is higher, and the gas prices are higher for everyone. And there are also block reorganization and breaks of consensus, which are no good. So it's not all that bad, because actually there are ways of preventing MEV. So I've looked, and there are lots of protocols that like allow users to prevent having MEV extracted from the trades in very complicated manners. But basically, like the simplest concept, I think, what you can do is you can like have a private mempools where you submit your transactions in a private manner and settle with the block creator. So you pay them something and they include your transaction, skipping the whole mempool. So having MEV extracted from your trades, avoiding having MEV extracted from your trades is possible, but if you are just using network without considering these things, you are probably losing money to some extent. I won't go through all the ways of preventing MEVs because these protocols are just complicated. But I just want to talk about one other risk of MEV happening. So in case of MEV Ethereum. So becoming Ethereum validator is costly. So I think you have to stake 32 ETH to become a solo validator, which is, I don't know how much, but a lot of money. 200,000 zloty or something like that. I'm not up to date with the prices, but it's a lot of money. So you can join staking pools instead. And larger pools have larger opportunities to extract MEVs, so they can earn more rewards for their stakers. So there's incentive for the users to join larger pools. But the problem with user joining larger pools is that eventually what could happen is that all of the consensus in the network could get organized around some couple of large pools, which is not very good for decentralization and not good for the stability of the network. So that's also concerning. But it's just one of the other of the disadvantages of the MEVs. So that's all from me. Are there any questions I maybe can answer?
Do you recommend any bots?
So I haven't really looked in very practical ways of doing that, but if you Google, there are lots of services that do that. I don't want to recommend anything because I haven't used any of these. I only read about MEV, but these exist. So. All right, if we don't have any more questions, I see the pizza has arrived. So thank you for listening to my talk and the talk of Kacper previously. And feel free to stay with us here in the office. So I have some closing remarks I wrote down. So there's a QR code just to the left of me. And if you want to become a speaker of these talks, of these on the future meetups like this, feel free to scan the QR code. There is an application form you can fill out, and we'll reach out to you. So feel free to scan the code, and we're looking forward to all the applications. And thank you for joining us today. I'm muted now. I assume you all follow us on some kind of social media to get updated on these kinds of meetup, but just continue following us there. There will be more in the future. Thank you.